Hello everyone, this is Feiyang, and this is my final project for reinforcement learning course. I did a literature review on adversarial robustness in deep reinforcement learning, focusing on cyber-physical systems like robots and self-driving cars. So, why did I choose this topic? I am really interested in how we can make RL agents safer in the real world. In my own research, I've been working on safety evaluation for embedded agents, and I noticed something really important. RL agents can get high rewards but still do dangerous things. For example, a robot might complete its task very efficiently but break safety rules along the way. This made me wonder if even small noise in the sensor readings can cause an agent to fail. How can we ever trust these systems in the real world? This is a question I wanted to explore, so I reviewed 11 papers from 2017 to 2024, covering 3 main areas: how to attack the RL agents, how to defend them, and how to measure their robustness. Let me start with the attacks. Huang et al. In 2017 were the first to show that adversarial attacks, which were originally designed for imaging classifiers, also work against RL policies. They tested on DQN, A3C, and TRPO, and all of them failed under very small perturbations. Then Lin et al. Came up with a smarter approach. Instead of attacking every single time step, they only attacked at key moments about 2500% of the time and got the same damage. This is much harder to detect. The most interesting thing is Galevi et al. From ICAR 2020. They didn't hack the sensors at all. Instead, they trained another agent to behave in the way that naturally confused the victim, and it worked, even against agents trained for over 500 million steps. Now, here's something that really bothers me about all these papers. They all measure how good an attack is by how much the reward drops. However, in the real world, reward is not the same stuff as safety, right? Think about it this way. A self-driving car that takes a long route has lower reward, but it's perfectly safe, right? However, a self-driving car that runs a red light also has lower reward, but it's totally a disaster, right? The reward number looks similar, but the consequences are completely different. I think this gap between reward and safety is the biggest issue in this field right now. On the defense side, I want to highlight 3 papers. First, Pinto et al. Proposed RARL, which trains the agent against a large adversary that pushes and disturbs it during training. The idea is that if the agent can handle the worst case disturbances, I guess it will also work very well in the real world, right? But interestingly, this sometimes even improves normal performance. Second, Zhang et al. At New Rips 2020 built a theoretical framework called SAMDP that gives us a principled way to train robust policies. But here is the twist. Kokmaz at AAAI 2023 found that regular training can sometimes produce more robust policies than adversary training. So, adversary training might actually give us a false sense of security. That's a pretty important worry. Okay, let's move on. I also ran 2 small experiments to support the review. In the first one, I trained a Q-learning agent on CardPaw and then added adversary noise to its observations. Even with very small noise, epsilon equals 0.05. The performance dropped by more than half. That is like minor GPS error crashing your whole system. And in the second experiment, I tried the strategic timing idea from Lin et al. I only attacked when the agent was uncertain about what to do next, and it turned out that attacking just 2500% of the time did almost the same damage as attacking all the time, but with way fewer attacks. This kind of attack would be really hard to catch in practice. Okay, looking ahead, I think the most important direction right now is to connect adversary robustness with formal safety specifications. Right now, defenses try to keep the reward very high, but what we really need is to make sure the agent never violates safety rules, even under the attack. That means using formal methods like temporal logic to define what safe or safety actually means, and then training agents to satisfy those specifications. Other promising directions include breaking robustness certification into small pieces, building runtime monitors that can detect attacks and switch to safe model, and testing robustness when multiple things go wrong at the same time. So in closing, the key message from this review is that we need to move beyond just protecting reward. We need to protect safety firstly, right? Small perturbations can break RL agents even in the smallest environments. For real-world systems, we need multiple layers of defense, robust training, attack detection, and formal guarantees all working together.